slope and deflection by for beams, but this time we're going to be using singularity functions. Okay, you'll see here that I've already put in table 12.2 from the Hibbler text with all the singularity functions in there. Make note that we have these pointy brackets, okay, and what these mean is the equation only works when x is greater than a. Otherwise, pointy brackets are equal to 0. Okay, so what this is a building. What we were doing with double integration is we were taking sections, drawing free body diagrams, and then drawing each part of the curve individually. What this is going to do is create one long equation that we build on as we move. Okay, let's get to examples because that will help. All right, my first example is going to be cantilevered. And I'm going to put a triangular load on here. With a maximum value of 3 kilonewtons per meter. And my cantilever is going to be 12 meters in length, and I've got it fixed all the way over here at A. Okay, and I wish to find the equation for the elastic curve using singularity functions. All right. Solution, as always, is going to start with reactions, and I've already solved for the reactions. My vertical reaction at A is 18 kilonewtons. My horizontal reaction at A is 0, and my moment is clockwise with 72 kilonewton meters. Okay? And I'm going to set the origin of the coordinates at the far left, just like the picture up here. See, all those x's here are measured from the left. Okay. So working from left to right and writing out my moment equation. By the way, as far as I'm concerned, the load equations and the shear equations are helpful information. But just like we were doing with double integration, we start with the moment equation and then we integrate from there. Okay, so the moment and the shear, you can see how they build up to the moment, but they're not going to come into play with this lecture today. All right, working from left to right, I start with my distributed load, and that is this fourth row here, distributed load, and its equation for the moment is little m over 6. Pointy brackets, I'm sure they have a special name, I'll look that up someday, x minus a cubed. So I need little m, which is the slope, okay? So coming over here, my slope is going to be little m is equal to rise over run, all right? Because I'm that way, I want to simplify it, so it's just 1/4. So there is my slope. So my moment here, equation for my distributed load is 1/4 divided by 6, pointy bracket, x minus a. A is where the whole thing starts. So it starts at 0 cubed, right? X ordinate a is equal to where it starts. See over here on this picture. Okay, you'll also notice, ladies and gentlemen, that they've got their distributed load drawn up and ours is acting down. So I need to put a negative sign there to show that ours is acting down. All right, then we move 12 meters and we run into 18 kilonewton point load. So come up here, point load is the second one here. And it is P, which is the point load, x minus a to the first power. So plus 18, because it is pointing up, bracket x minus 12 to the first power. And then the last one we have here is a moment. You can see here that the moment here is acting clockwise as well. So we need the magnitude of the moment plus 72 times x minus a. It occurs at 12. 0 power, right? 0. 0. Okay, now I know what some of y'all are noticing. You said, I said earlier that it only works when x is greater than a, and there is no way we're ever going to be greater than 12. So these last two components are unnecessary. You are correct. They are unnecessary. They always will equal 0. But because this is new information and we are starting on the green circle bunny slope, okay, I'm going to put them there so that you know we're not ignoring them. They still do exist as forces. They're just not going to come into play for slope and deflection. Okay, I'm going to clean this up a tiny bit. This is going to be 1 over 24. So my slope equation, theta EI, is equal to negative, oh, I kind of did this the hard way. Okay, that's all right. 1 over 96 times x minus 0 to the fourth plus 18 divided by 2 x minus 12 squared plus 72 x minus 12 1 plus our constant of integration. Yes, we're still double integrating, but that's not what the method is called. Then we have our elastic curve equation, which is minus 1 over 480 times x minus 0 to the fifth plus 18 divided by 6 x minus 12 cubed plus 72 divided by 2 x minus 12 squared plus c1x plus c2. So now that we have our elastic curve equation and our slope equation, okay, we can use boundary conditions and continuity conditions to solve for the constants of integration. Okay, what is fantastic about a fixed end is that slope and deflection both equal to 0 at the fixed end. Theta and v equal to 0 at the fixed end. And the fixed end is located at x is equal to 12. Okay, and that is little v for vertical deviation, not capital V for shear. So solving for slope first, because that's only one unknown, I have 0 is equal to negative 1 over 96 times 12 minus 0. Notice how I have normal parentheses now because we're plugging in a value that is greater than a. And then plus 0 because 12 is equal to 12 plus C1. And we will find that the constant of integration 1 is equal to 216. And then I'm going to, that's my slope, and then my vertical deviation is also equal to 0. It is minus 1 over 480 times 12 minus 0 to the fifth power plus 0 plus 0 plus C1, which is 216, times 12 plus C2. So my constant of integration 2 is equal to negative 2073.6. All right. So cleaning this up for my final answer, I would say VEI Do I want both equations or just equation for the elastic curve? Okay. Is equal to negative 1 over 480 x minus 0 to the 5th plus 216x minus 2073.6, and this will still be in kilonewton meters cubed. This is my answer. Let's see if I can box that in.